Isaac Newton was a brilliant scientist who lived centuries ago. He revolutionized our understanding of the universe. Newton's laws of motion are fundamental principles that govern the motion of objects. Everything in the universe, from the smallest particles to the largest stars, obeys these laws. They explain why things move the way they do. Understanding these laws allows us to predict and explain the motion of objects all around us. Before Newton, people didn't fully understand how objects moved. They thought that objects in motion would naturally slow down and stop. Newton showed that objects have a tendency to keep doing what they're already doing. He proved that a force is needed to change an object's motion. These powerful ideas form the bedrock of classical physics. They are essential for understanding our physical world. In the following sections, we will embark on a journey to explore each of Newton's laws. We will see how they play out in our everyday experiences. Newton's first law of motion is also known as the law of inertia. This law states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. This means that objects resist changes in their state of motion.
Imagine a book lying still on a table. The book will remain at rest unless someone or something applies a force to it. Now picture a bus moving down the road at a constant speed. The passengers inside the bus are also moving at the same speed. If the bus suddenly brakes, the passengers will continue moving forward at the original speed due to inertia. This is why seatbelts are crucial in vehicles. Consider a soccer ball rolling across a field. The ball will continue rolling in a straight line at the same speed unless an external force, such as friction from the grass or a player's kick, acts upon it. Inertia is the tendency of an object to resist changes in its motion.
Newton's second law of motion explores the relationship between force, mass, and acceleration. It states that the acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. This law is often summarized in the famous equation F equals sine ma, where F represents force, m represents mass, and a represents acceleration.
Let's break this down with a simple example, pushing a shopping cart. When you push an empty shopping cart, it accelerates easily. However, if you try pushing a cart full of groceries with the same force, it will accelerate much slower. This is because the full cart has a larger mass. Consider kicking a football. The harder you kick the ball, the faster it will accelerate. Similarly, if you apply the same force to kick a heavier ball, it will accelerate less than a lighter ball. The acceleration of a car is another example of Newton's second law in action. When you press down on the gas pedal, the car's engine generates a force that propels it forward. The greater the force from the engine, the faster the car will accelerate. Conversely, when you apply the brakes generate a force that opposes the car's motion, causing it to decelerate.
Section 4. The law of action-reaction. Every action has an equal and opposite reaction. Newton's third law of motion states that for every action there is an equal and opposite reaction.
In other words, when one object exerts a force on a second object, the second object simultaneously exerts an equal and opposite force on the first object.
Imagine jumping off a small boat onto a dock. As you push off the boat with your legs, which is the action, the boat pushes back on you with an equal and opposite force, the reaction. This is why you move forward towards the dock, and the boat moves backward away from it.
The launch of a rocket is a dramatic illustration of Newton's third law. The rocket expels hot gases downward, which is the action, and the gases exert an equal and opposite force on the rocket, propelling it upward, which is the reaction.
Even the simple act of walking involves Newton's third law. When you walk, you push backward against the ground with your foot, the action. The ground in turn exerts an equal and opposite force forward on your foot, the reaction, propelling you forward.
Section 5. Newton's laws in action. From everyday life to the cosmos. Newton's laws of motion are not just abstract concepts confined to textbooks.
They are constantly at play in our daily lives and throughout the universe.
Every time you throw a ball, drive a car, or simply sit still, you are experiencing the principles of Newtonian mechanics. These laws explain why objects fall to the ground at the same rate, regardless of their mass, in the absence of air resistance.
They underpin the design of bridges, buildings, and airplanes, ensuring their structural integrity and stability.
Beyond our planet, Newton's laws govern the motion of celestial objects. They allow us to predict the orbits of planets, the phases of the moon, and the trajectories of comets. By understanding the forces acting upon these objects, we can unravel the mysteries of the cosmos.
Section 6. The enduring legacy of Newton's laws, a foundation for modern science. Newton's laws of motion have had a profound and lasting impact on our understanding of the universe. They provided a unified framework for explaining motion and laid the foundation for classical mechanics. His work paved the way for groundbreaking advancements in physics, astronomy, and engineering. From the development of calculus to the exploration of space, Newton's legacy continues to shape our scientific endeavors. While Einstein's theories of relativity introduced modifications to Newton's laws at very high speeds and in strong gravitational fields, Newton's laws remain incredibly accurate and useful for most everyday applications. They are a testament to the power of observation, experimentation, and the human mind's ability to decipher the laws of nature.
Section 7. Conclusion. Newton's universe. A universe governed by laws. Isaac Newton's laws of motion are fundamental principles that govern the motion of objects in our universe. From the inertia of a book on a table to the launch of a rocket into space, these laws are constantly at play, shaping our understanding of the physical world. They provide a framework for predicting and explaining motion, and have driven centuries of scientific and technological advancements. As we continue to explore the vast expanse of the cosmos and delve deeper into the subatomic realm, Newton's laws remain essential tools for unraveling the mysteries of the universe. They stand as a testament to the power of human curiosity, ingenuity, and the enduring quest to understand the fundamental laws that govern our existence.